So there's going to be a lot of theory in the multiple choice from chapters 7 and 8. So 7, we talked about why you can prove a bell shape with means and proportions, right? And so with the confidence intervals, let's see. So here's a question, right? What's my new favorite saying going to be? Everything else remaining equal. What happens to your confidence interval as your confidence level increases? It gets wider, right? Your interval got wider. It went from, if you look at it, 30.6 to 33.4, and then it went down to 30.3 to 33.6, and it went to 29 point something up to 34 point something. It got wider as you increased your confidence, because everything else remaining equal, if you want to be more confident, you just got to make it wider and you're more likely to catch the right answer. Okay, so everything else remaining equal, as you increased your confidence, what happened to your margin of error? Okay, how wide is an interval?
2 margins of error.
2 margin of errors. So as your confidence got bigger, we said the interval got wider. If the interval got wider and every interval is 2 margin of errors, the margin of error must have gotten bigger. It could have gotten smaller. If the margin of error got smaller, the interval would have been narrower. Okay, so everything else remaining equal, if you increase your confidence, your interval becomes wider because your margin of error is bigger. Right? A wider interval has to go with a bigger margin of error. There's no way to get a wider interval if your margin of error gets smaller. It's impossible. Right? Okay, what happened to your standard error? As you became, everything else remaining equal, as you became more confident, what happened to your standard error? It stayed the same. Right? What you changed as you went down from one to the next, right? This is your margin of error. All of this. This is your standard error. The only thing that changed as you went down was your z-score, right? Based on, you did not change this at all. Okay, so that could be a complicated multiple choice question. Everything else remaining equal. As you increase your confidence, and then there'll be a whole variety, but the right answer would be A, the standard error stays the same. B, no, not an A, B, and C, but there'll be 3. A would say the standard error stays the same, the margin of error gets bigger, the confidence interval gets wider. That would be the right answer, but there'll be a lot of other variations down here. So you need to know all what happens to the parts in a theory question, maybe when there's no numbers involved. Right, so you've got to think about, if you're changing your confidence level, what part of the formula changes? And is that part getting bigger or smaller? And what gets affected? So think it through. Okay, so everything else remaining equal, as we increase our confidence level, it gets wider. The opposite is true. Right, if you'd have done something for 95% confidence and it's really wide, and you want to make it narrower, you might do it 90% confident if that's good enough for you. Okay, so we're going to start to look at t-scores. Oh, I just moved something. What did I just do? So now, what happens if none of those 3, what are those 3 proofs again that prove a z-score is bell-shaped? The underlying population is bell-shaped and sigma's given. N is greater than or equal to 30 and sigma's given. N is more than 100. If not, what, yes?
Can we just go over really, really quick what it means when the underlying population is 1?
Yes. like if I said the time any student takes, like you're told the distribution's normal. See, most all the questions are not told that the distribution's normal.
Yeah.
The underlying, that means like if this is how long might you, GBS 221 students time on a test, okay, and on average you take 65 minutes. But if I said it was bell-shaped, right, with a standard deviation of 5 minutes, or not, right, then this would be 80 minutes, and this would be 50 minutes, right? But I'd have to say the underlying population's bell-shaped. Okay. Now I'm going to take samples of 10 students. Then as long as I've got sigma, then I know that the sampling distribution will also be this bell-shaped. The sampling distribution, remember, is showing me all the possible values of x bar I could get. So if the individual population values of x is bell-shaped, this is more likely to be bell-shaped. But I showed you other ones where the underlying population was not bell-shaped. And then when we took samples of 2, it looked like that.
Yeah.
But by the time we got to samples of 5, it was bell-shaped. But if this one had started out bell-shaped, this would have, been bell-shaped all the way down.
Okay.
Yeah. Does that make sense?
Yeah, I remember that.
Did you have a question?
Oh, no, that was.
That kind of answered it too? Okay. So let's say none of those 3 things are true. And you're not allowed to use a z-score, right? So if none of those 3 things are true, your data's not that fabulous. Your sample's not more than 100, you don't have sigma, right? For some reason, your sample's not really fabulous. A t-score is a punishment. The finite correction factor, that was a reward for taking a big sample. You having to use a t-score, that's a punishment. You got kind of a crappy sample. Got a little sample, you've only got S and not sigma. For some reason, you don't have a great sample. Sometimes you don't take great samples. Why would I not take a great sample? Why would I take a great sample every time? Time? What else? Not right? What if, there's this really nice color. Was it you I was talking about this really? On my house in California, down the street, there's this car. My husband has to secretly take a picture of when he goes by. What's it called? A McLaren. Okay. My husband said, I think they bought the cheap version. It's $250,000. The expensive one's $800,000 for one. We probably don't want to crash test too many of those because they don't make very many of them. To start, you don't want to crash test a sample of 100. Because they don't make that many every year, right? This person's McLaren. It's like purple foil. That's what it's like. It shines off their white garage. They leave it outside. I'm like, what has got to be in your garage that's more valuable than your $800,000 car? But they park it in the driveway. Anyway. There are some things that are very expensive, right, that are ruined by testing, that you don't want to test them on. So you have a small sample. And as a result, you're going to be punished, though, because your data's not going to be as accurate. You're going to have great data, you're going to use the t-score, and that is a punishment. Okay? Using a t-score is a punishment. Now, I know you think it's almost like we gang up against you to do this, but we don't. But if you remember from your Z tables, right, the Z's are here, correct? And then here are the areas, or the probabilities, right? To the left, do you agree? That was when we got to use the Z-score. So now I'm going to introduce you to the T tables. It's completely opposite. Okay, so on the t-tables, these are the t-scores. Up here are the areas. Guess what? To the right. But it does say it. Okay, it does say it. Area to the right. And then this is something new down here called the degrees of freedom. And the degrees of freedom are real, and it's a formula on your formula sheet, but your degrees of freedom are n minus 1. Okay? You can read about it in the book if you want to read what it means. But it's like, you can pick 24 numbers, but the 25th one will be decided for you. Alright, so if you're looking at a t distribution, you need to know the degrees of freedom, which is n minus 1. Okay, and then, so let's look at the tables. It comes right after our z tables. There are t tables. So it's got degrees of freedom in the left column. It's got the areas, it says in the upper tail, okay, across the top. And it goes on to 3 pages. It goes up to degrees of freedom is 100. If degrees of freedom are 100, what's n?
101.
101. So really I wouldn't use it, right? Because if n's 101, wouldn't that qualify me for a z-score? Right? So, but they're there for us to show you, we'll have that coming up, to show you why. But why, I'll tell you what happened. Everything else remaining equal. A t-score is bigger than its corresponding z-score, whatever sample size. Okay, if you want to be 95% confident, when you used a z-score, you used, sorry, did I get you again?
No.
1.96, right? That's the z-score for when we want to be 95% confident. When we look up, if we look up some other here, the t-score will be more than 1.96, because remember, it's a punishment. And so if we're going to have x bar plus and minus, instead of z, we're going to have t alpha over 2, right? And then we've got the standard deviation here, okay? So this is going to be bigger than the z-score, which will make my margin of error what? Bigger also, which will make my confidence interval wider. If this is bigger, then the interval's got to be wider, right? Because there's 2 of them. So this is going to be bigger, making this bigger, because my data's not so great. My data's pretty crappy. I got a little sample, it's not real accurate, I've only got S, okay? So this t-score is going to be bigger than its corresponding z-score. Alright, so let me do a question with you and I'll show you. So you can see here, the only difference in the formula, okay, well there's a couple. And I will tell you that I put a T here and I put an S here. Because often, the reason you have to use a t-score is because you've only got S, which is what? Sample standard deviation. You don't have sigma, which is the population standard deviation. You've only got the sample standard deviation. Now that's not always the case. There are times when I have sigma that I have to use a t-score. When? Right, if n's less than 30, right? If it said n is 25 and sigma is 12, that doesn't qualify me to use a z-score, does it? It doesn't match any of them. So there are times when you have a t-score that this is sigma, right? But I didn't want to write more formulas for you to pick from. There are times, to be honest with you, this is the other formula you've got written, right? But aren't there times when you can use a z-score when that can be S? If you've got S is 12, when can I use a z-score? Couldn't I use a z-score when I've got S? Sure. So there, you can also have, but then I'd have to write, instead of having 2 formulas, I write 4. So I wrote the ones in the main ones that you use. But do know that there is a time that you can use a z-score when you have S, even though the formula says sigma. And there are times that you have to use a t-score when you have sigma. So you just have to keep, you know, remembering your rules and just decide, can I use a z-score or not? Okay, but else it's the same formula, right? Except for we're going to be looking up a t instead of a z. Now we still have the same rule. When do I get t? What's this called here? Finite correction factor. Okay, factor. What did you say?
We got it wrong.
Figure.
Calculator.
Finite correction factor. When do I get to use it? Everyone remembers 5%, but what 5% what? When your sample size is more than 5% of the population size. Okay? So here's a question. It says, I want you to write down with the correct symbols the information that's been given. A reporter for a student newspaper is writing an article on the cost of off-campus housing. A sample of 16 efficiency apartments within a half-mile of campus resulted in a sample mean of $650 per month and a sample standard deviation of $55. Provided 95% confidence interval estimate of the mean rent per month for the population of efficiency apartments within a half-mile of campus. Okay, what have we been given? Tell me what to write down. Little n is 16. Apartment.
X bar deviation
X bar
equals $650.
Good, you're getting your units in.
Standard deviation.
What kind of sample standard? What's the standard deviation? S, right? It's a sample standard deviation. What is it?
55.
$55.
Alpha is the 05.
Alpha
0.05.
05. Got it? Okay. So proof. There isn't one. Doesn't say the underlying population is bell-shaped. N's not greater than or equal to 30. N's not more than 100, right? There's no proof. Therefore, I have to use the t-score. So it's x bar plus and minus t, alpha divided by 2, s over the square root of n. Do I get to use the finite correction factor?
You don't have the big N.
I don't even have a big N, so I couldn't fill it in, even if I wanted to. Okay, so the x bar, this is 650, plus and minus, we'll look this up in a minute, and this is $55 over the square root of 16. Yes? Okay, so let's go to our tables. Here's something else you could fill in over here, since we know it's a t-score. What are my degrees of freedom?
-1. So it's 15.
N minus 1. 15. Okay. So we're going to go to our booklets, and in the first column, we're going to go to degrees of freedom of 15. Now, alpha's 0.05, right? So that meant we wanted to be 95% confident, agreed?
Mm.
And it means that there's 2.5% in each tail. So what is the area in the upper tail if you want to be 95% confident? You go to 0.025 up here. You still are looking, right, for the t for alpha divided by 2, correct? The formula says the T of alpha divided by 2. So we could say, right, that alpha divided by 2 is 0.025. So go to 0.025, go to degrees of freedom of 15, and what is the T-score? 2.131. That's bigger than that 1.96, isn't it? Because that's our punishment. That's our punishment for having a tiddly little sample, right? So because this is not 1.96, it's going to make this bigger, correct? What's this whole thing called right here? What's this called right here? Right. So what happened to the standard error? Nothing, but using a T-score makes this my margin of error bigger, which makes my confidence interval wider. Got it? Yes? So if you put it in your, you do the math, okay, you get 650 plus and minus 29.3. So you'd say you're 95% confident that the population mean rent is between $620.70, $679.30. Does that mean that if I want to buy rent an apartment, but I want to spend $1,000, will I be able to find one? What if I want a fancy apartment? Can I find one? Possibly, right? Couldn't it mean that there's an apartment building that are $1,000 each for every apartment, and another apartment building that they're $300 each? What would that make them on average? $650, right? So that it could be that's the case, couldn't it? So remember that this is just you trying to find the average. It doesn't mean that there's one apartment for rent between these two prices. It might mean that they're $1,000 or $300, but on average, they're between here. They use a lot of this type of data when they do like Scottsdale's the most livable city. They have to provide dates, prices, and all this kind of stuff about housing where we live and all of the different things that they have. So they use a lot of this type of data in real estate, actually. All right, when we come back on Thursday, I'm keeping today's Monday, we'll get back to this.